Good evening, students. Now let's move on to next theorem. Let f belong to R of alpha on closed interval a comma b. F is less than or equal to capital M and greater than or equal to M. Means f is bounded and phi is continuous on closed interval small m comma capital M. H of x is the composition of phi and f on closed interval a comma b. Then h, which is the composition of phi and f, is Riemann-Stieltjes integrable, or we need to show that h belongs to R of alpha on closed interval a comma b. So what is the given data here? The given data is that the function f is Riemann-Stieltjes integrable on closed interval ab and it is bounded on closed interval ab. And another function phi is continuous on closed interval small m comma capital M. Then the function h of x, which is the composition of phi and f on closed interval ab, is a Riemann-Stieltjes integrable. So this is what we need to prove. Now let's move on to the proof. Okay. Since phi is continuous on closed interval m comma m, see it's actually given. Phi is continuous on closed interval m comma m. So since phi is continuous on closed interval m comma n, it implies that phi is uniformly continuous on closed interval m comma m. See, we know that any function which is continuous on closed interval is uniformly continuous on that closed interval. So it is known. So using that fact, we write phi is uniformly continuous on closed interval m comma m. And now using the definition of uniform continuity, it implies for given epsilon positive, there exists delta positive such that mod of phi s minus phi t less than epsilon whenever mod s minus t less than delta. And this holds for all s comma t belonging to m comma capital M. So whenever this is less than delta, the difference between their images is less than epsilon. And this holds for each and every element in the interval. So that is the definition of uniform continuity. And also, since f belongs to R of alpha on closed interval a comma b, there exists a partition P such that difference between the upper sum and lower sum is less than or epsilon, and I have taken that epsilon as delta square. Okay. Now I have used the definition of upper sum and lower sum. It is actually summation mi delta fi minus summation small mi delta fi. I have taken delta alpha I common and I have written summation I equal to 1 to n mi minus small mi into delta alpha I. Since this is less than delta square, this is also less than delta square. And here this capital Mi is the supremum of f of x in the interval xi minus 1 comma xi. And the small mi is the infimum of f of x on the interval xi minus 1 comma xi. And since phi is continuous on closed interval m comma m, phi is bounded on closed interval m comma m. Okay, since it is bounded, see here, there exists k belong to R such that mod phi of t is less than or equal to k. This is for all t belong to closed interval m comma capital M. And since this is less than or equal to k, see, in place of t, I can also take f of x. Why? Because this f of x also lies between m and capital M. That is, f of x belongs to closed interval m comma m. So here this is true for all t belongs to closed interval m comma m. So there is no harm in taking f of x in place of t, as f of x also belongs to the same interval m comma m. Since this is true for all t belonging to this, it should be true for f of x also, which belongs to the same interval m comma m. So in place of t, I am writing f of x. So mod phi of f of x is less than or equal to k, and this is for all f of x belonging to this closed interval m comma m, or for all x belonging to closed interval a comma b. Okay, see here I am picking the value of x from closed interval a comma b, and f of x lies here. So this is true for all f of x belonging to this interval, or for all x belonging to this interval. It's one and the same. Okay, and also given h of x, h of x is equal to phi of f of x. Okay, phi of f of x. So here I can write phi of f of x as h of x. Okay, so mod h of x is less than or equal to k for all x belong to closed interval ab. See, this means the function h is bounded on closed interval ab. Okay, it means the bounds of h exist. Okay, so its bound exists means I can take its supremum and infimum. Okay, so here let mi star be the infimum of h of x in this particular interval, and capital Mi star be the supremum of h of x for all x belong to this interval. Okay, see, I am now dividing I equal to 1 to n into two classes as a and b. Here in a, I am containing all I such that the difference between mi minus mi is less than delta. And here in b, I am collecting all I such that the difference between these two is greater than or equal to delta. See, I am taking one number delta, and this difference must be either less than delta or greater than delta or equal to delta. So what I am doing, I am dividing that class into two. So here, wherever the difference between mi and small mi is less than delta, I am putting those values of I here in a. And wherever I am getting the difference between capital Mi and small mi greater than or equal to delta, I am collecting those values of I here in class B. So this is what I am doing. Okay, so that if I belongs to A, what happens? If I belongs to A, then the difference between this is less than delta. Then by the definition of uniform continuity, I have this. So since the difference between these two is less than delta, then the mod phi of mi minus phi of small mi should be less than epsilon. Okay, and since this f lies between, see here, since f lies between small m and capital M, then the infimum and supremum of f of each and every subinterval should also lie between this. Okay, so here, see here, phi of mi minus phi of mi is less than epsilon implies, see, actually this capital Mi is the supremum of f of x in the interval xi minus 1 comma xi, and this small mi is the infimum of f of x in the interval xi minus 1 comma xi. So phi of f of xi minus phi of f of xi minus 1 is less than epsilon. Why? Because this value of f lies between m and capital M. And here these values also lie between m and capital M. Okay, so phi of f of xi is nothing but h of xi. Phi of f of xi minus 1 is nothing but h of xi minus 1. So mod of this less than epsilon. See here, phi of f of xi is nothing but h of xi, and phi of f of xi minus 1 is h of xi minus 1. So now the difference between this is less than epsilon for all I. Okay, so that is actually the definition of uniform continuity. So this holds for all I. And now if this holds for all I, then it must hold for this also. This is the supremum of h of x in the interval xi minus 1 comma xi, and this is the infimum of h of x in the interval xi minus 1 comma xi. So if this is true for all I, then it must be true for this also. Okay, see here, if this mod of this is less than epsilon, then obviously mi star minus mi star is also less than epsilon, because mod is only less than epsilon. So obviously this m, after removing mod also that also will be less than epsilon. Name this as 3. Okay, now if I belongs to B, then mi minus mi is greater than or equal to delta. Okay, so this is, we have divided into two classes. So according to that, if I belongs to B, then mi minus mi should be greater than or equal to delta. That is, summation I equal to 1 to n, mi minus mi, delta alpha I is greater than or equal to summation I equal to 1 to n. So in place of mi minus mi, I have written greater than or equal to delta. And the summation I equal to 1 to n delta into delta alpha I, obviously it will be greater than or equal to summation for only I belong to B. So this is for all I equal to 1 to n, and this is only for I belong to B. So obviously this sum will be greater than or equal to this sum. Okay. Then if this is greater than or equal to this, then obviously this will be less than or equal to this. So summation I belong to B, delta into delta alpha I is less than or equal to summation I equal to 1 to n into mi minus mi into delta alpha I. And we know that this is less than delta square. So we have written that in the equation 2. See here, this is less than delta square implies this summation, entire summation I equal to 1 to n is less than delta square. So I am using that here. So this is less than delta square. If this overall I equal to 1 to n, that sum is only less than delta square, means obviously this sum which is less than this will also be less than delta square. Delta on both sides will get cancelled and you will be left with only one delta on the RHS. So name this as equation 4. So now to prove that H belongs to power of alpha on closed interval AB. Okay, we need to prove that now. Okay, since H is bounded on closed interval AB, see that implies mod H of x is less than or equal to k for all x belong to closed interval AB. So if mod x is hx is less than or equal to k, it implies minus k less than or equal to hx less than or equal to k for all x belong to closed interval AB. And since hx is in between minus k and k for all x belong to AB, then this small mi star and capital Mi star, which is the infimum and supremum of h of x, also lies between minus k and plus k. Okay, and this implies mi star minus mi star is less than or equal to k plus k, which is 2k. And this is less than or equal to this, so this minus this is greater than or equal to 0. Okay, so name this as phi. Now consider u of p comma h comma alpha minus L of p comma h comma alpha. See, now we need to prove that h belongs to R of alpha. So instead of f, I have taken h here. So the upper sum minus the lower sum, okay, of h, okay, with respect to partition p and alpha is equal to summation I equal to 1 to n capital Mi star minus small mi star into delta alpha I. So here we have split this into two summations. Okay, see here, this is less than epsilon for I belongs to A. So you can see that here in equation 3, for I belong to A, mi star minus small mi star is less than epsilon. So I have used equation 3. And remaining I have written like that only. Summation delta alpha I for I belong to A. And next plus, see here I have used equation 5. Okay, so that will be less than or equal to 2k summation I belong to be delta alpha I. And here in this case, I have written this as alpha b minus alpha a. And in here, this case, and here in this case, where I belong to b, I have used this one. I have used this one, equation 4. So using equation 4, I have this is less than delta. Okay, so epsilon as it is, and this I have written as alpha b minus alpha a. Okay, see, once I expand this, I will get this. Okay, and plus 2k into delta, which is equal to epsilon star. This implies the difference is less than epsilon star. Okay, see here I have taken this as epsilon star, say, and I have proved that the difference between upper sum and lower sum is less than epsilon star, and therefore h belongs to R of alpha on closed interval AB, and hence the proof. Thank you.